So this paper is titled Learning Transferable Visual Models from Natural Language Supervision. There is a lot packed into the title. And so let us decompose this step by step and see what it means. We have to unpack it. What are visual models? We'll see as we do this. We do know that, if you remember, we covered VIT, right? Visual transformers, which was the, how does a visual transformer work? It works by taking an image, slicing it up into patches, 16 by 16 patches, plus 16 pixel patches, putting all those patches together, right? Rendering each of the patches into a vector. And from them, through proper some projection, making them into like embedding input. Right. So each patch is essentially like a token for a transform. We recall that, right? So the summary is that we can take a VIT, we can take this and feed it an image, just as we are used to feeding it word tokens. Now we can feed it visual tokens. And then the rest of the encoder takes over, BERT-like encoder takes over. And what will the encoder produce? So encoder, given a picture, given this picture that becomes this, what will it produce? It will, of course, you'll also have a CLS token in the beginning. It will produce hidden states, right? Hidden states for CLS, hidden state for H1. It will produce the logits vectors, N, for each of these patches, the vectors for each of these. Now, suppose you have a text. It goes through a standard encoder, text encoder. The cow jumped over the moon. What will happen? These tokens will again become vectors. They will go in. You will again get your same things. H prime, suppose it has K tokens, right? Those latent vectors will come out. These are your latent representations. Your latents come out from both of these. Now, this paper asks one thing. Suppose the words, the textual description, and the image are saying the same thing. Can we teach a machine to produce an embedding vector that is proximal to the two embedding vectors to be proximal to each other? Can we do that? Are we together? Can we do it in such a way that the vector for the image and the vector for the text, if the two are together, they are very close? Make sense? Right? So that should take you back to your contrastive learning. Remember the triplet laws? Contrastive learning. What would you do in a contrastive learning? You would take a sentence, A, you would take something similar, and you would take something random. And then your loss function would be, what would it do? It would maximize the sim between A and the similar, what you know to be a similar text, and minimize the similarity between A and R. right? What it would mean is, if the similarity is in terms of cosine, then in the vector space, you want A vector and the S vector to be proximal and the random vector to be as far as possible. Does that make sense? The hidden states for these to be, actually, let me put H here. H embedding of these to be as far as possible. Once you get that idea, you realize that, guess what VIT gives us? VIT gives us an ability to treat images interoperably with text, isn't it? So what I can do is I can take A to come from an image, S to be the description of the image, or just throw in some junk, right? Some random text. So I could do that. Does that make sense? Right? I could easily do that, right? And that is the main idea of this text. What it is saying is, what if we could align? Let's read the figure 1, summary of our approach. While standard image models jointly train an image feature extractor and a linear classifier to predict some label. So what used to happen is, suppose you had a cat and you want to know what is this image about. You would typically use a classifier that used to predict into a vocabulary. It would produce a probability of a cat. Right? Those were discriminative tasks, discriminate classifiers. But what this thing is saying, no, we don't, there's an alternate way. Suppose I give you an image and it produced for you, aligned it with the description of this. Yeah, and did that. Or if I gave you a description, a text, and you could pull out an image that is aligned with it. Wouldn't that be amazing? Isn't it? So that is the main thing. Let's read this thing more carefully. While standard image model, so by standard means way back when, not today, way back when. No. In ancient history, like this is 2020, this is 2021. Jointly train an image extractor and a linear classifier to predict some label, cat, dog, whatever. The clip, on the other hand, yes, let me do that. Oh, touches. Why am I not able to increase the font? Maybe it is at its maximum, is it? Okay, no, hang on. I'll be able to do that. Yeah. Little bit less. Okay, let's stick to this. So you're saying that clip, on the other hand, jointly trains an image encoder and a text encoder to predict the correct pairing of a batch of image text training examples. So forget about the batch word. It knows how to align. You know, the way I explained to you in pictures, it will do this, right? So at test time, the learned text encoder synthesizes a zero-shot linear classifier by embedding the names or descriptions of the dataset. But we'll come to that a little bit later. How does it do that? So you can imagine, you can see image encoder is producing its logits, text encoder is producing its logits, right? And we'll do some magic. We'll do this contrastive learning thing. Now, suppose you want to tell this picture whether it is a dog, a bird, a plane, or a car, let's say. So what could you do? You could create 4 sentences, the photo of a dog, the photo of a car, the photo of, you could just write some text description. And what you could do is, once this machine is trained, you could pass your image through this encoder and the text also through the appropriate text encoder, and basically say, if I have this image vector, image, I could do this. I could play this game. I could do each one of these vectors, right? A candidate, let me just call it candidate plane, candidate car, candidate dog vector, and candidate bird vector. I could find the inner product, similarity measure, and what would happen? Whichever vector it is closest to, would that be the answer? Isn't it? Right? And therefore, if I were to train this model, it would act as an amazing classifier also. It turns out that when the CLIP paper was written, people thought it's a big deal that you could classify using a completely different method. Yeah. This, yes, it is a valid classifier, but in hindsight, that is not the biggest use of this particular approach. You'll see, as you know, we used it in our search engine, multimodal search and so forth, right? And it is the beginning of a lot of interesting things that we're going to cover today going forward. Now, what is this paper, or how does this paper go about doing it? Let's read the abstract. The state-of-the-art computer vision systems are trained to predict a fixed set of determined object categories. This restricted form of supervision. What does the word supervision mean in the title? Supervised learning. That you have to train the model. Train the model with the loss function. Whenever you train the model with the loss function, it's supervision. Supervising.
So the label is given for that?
Yeah. So the whole question is, you have to assume that A and S are given. Image and its description are given. How it is used, I'll tell you in a moment. So actually, how about this? I'll just skip this because it goes on and talks a lot about things. It is an amazing job, but in hindsight, I will use a slightly different way of explaining this paper because so many years have passed. It's a foundational paper. How do you train a model like this? And where does the word CLIP stand for? CLIP. Contrastive loss. I could be image. P for pre-training. Right? So does it make sense now? So the moment you write this equation, it becomes obvious what we are doing. Are we doing contrastive loss? And image is A is the image. And what will it lead to? If I train a machine with this model, with this, I'll end up with a pre-trained model. But here is the problem. I need a lot of combinations of images and text. Who's going to do that? Who is going to create? Because pre-training takes gazillions of data points, right? You're taking a big transformer model, you're pre-training it. Where do we get that from? Any clues? It turns out that the web developers have been pretty helpful, folks. If you look at any website, what you will notice is that they will have, yes, they will have the tag literally like this, IMG. Exactly. Let's say dog.png, something like that. And there is an alt tag. Right? So guys, do you notice that you got your A? A is this. A textual description of this is your similar. Right? And random is easy. Just pick up something and throw it in. So you can do your contrastive loss learning. So what they did is, because people had scraped the web, it was HTML pages are filled with these. There's a problem though. Most people forget to put alt, but you'll still get a reasonable proportion of things with alt.
Image name not required to be same name.
Yeah, they don't. It could be just x.png. Right? So you could harvest the image to feed into the image encoder. You could harvest the text to feed into the text encoder. Now, there are a couple of problems. The problems that in reality people faced. One was that alt is often missing. So obviously you can't assume that every single image tag on the web is useful, but you'll still get a pretty large crowd. The other problem that people face, which is a bit of a nuisance.
So majority of that nowadays is like the system generated HTML pages.
That is right. That is right. But even then, they encourage you to put alt. So people do that. It's a good practice to do that. But what people do is they use the alt for SEO, search engine optimization. So even though it's a dog, suppose you sell, I don't know, dog food. It will just contain dog food, nutrition, etc. You will have a comma separated list of junk. So you have to be able to tell that this may be SEO eliminated. You can't. So the initial data set that the clip guys gathered was actually very noisy. Right? Subsequent papers, as we will do in the BLIP paper, they went out and found a way to clean it up. Right? But nevertheless, when they trained the machine with this, the model that came out was the clip model, which is the model that you used, right? And it was amazingly effective. It just shook everybody. Remember, this is 2021, right? When this came out, people went like, wow. Remember, at those times, the big things that were coming out were clip, and right after a little while came DALL-E, and so on and so forth. Those were the things. And by the way, you'll cover all of those. We'll be covering DALL-E in detail. Right?
Well, no, because so I think like economy says we are imposed by the rule that you are making these channels if you want SEO traffic. We didn't realize that all data we took it for
Yeah. Right, yeah. So guys, this is all there is to clip. And its effect, you guys have already seen in your Jupyter notebook, isn't it? Wasn't it amazing that you would say a house by a lake and it would do that? Right? You would say love for a dog, it would capture emotion. When was the last time a search engine could capture that? Right? And so because of this paper, you could do multimodal search, at least in images. Imperfectly, but you could do that. There was a limitation though. See, the alt tags are short text, isn't it? So because of that, you could only give relatively, like if you couldn't do big text, those limitations of in subsequent research has been removed. Today, we are much smarter about these things, but nevertheless, it was an example of zero-shot learning, because once you do that, once you have trained your machine with thousands and thousands of images, even if you give it a completely new image, it still works, isn't it? You give it a completely new caption and search index, it still works, and you guys saw that. Go ahead.
Still on the description. That be detailed or short?
For clip, actually, what happens is that because it scraped this, you look at this image, they went through billions of Instagram photos and this and that, right? People just put one-liners, which was a limitation of clip. It didn't handle long text that well. But the world has changed. I mean, a clip is the beginning. I'm just introducing you to just the beginning of a new world. I mean, see, guys, these papers that we are going to do, and we have been doing, if you remember, we did sentence BERT, we did transformer. Each of these papers in our field has been major milestone. They have defined this field.
The point is, this is beginning, and will it help if we had more clear description of the data?
Yes. Yeah, absolutely. In fact, today we are in the world, as you will do. In fact, today itself, I'll do BLIP in the afternoon. It will make a big improvement over clip. There's BLIP, there's BLIP 2, right? There's Lava, there's Lava 2, Lava 3, I mean, Lava 2, 1.5, then 2, and so on and so forth. Go ahead.
Maybe the random vector, right? For contrastive loss.
Yeah.
Is it from the image vector?
No, just some random
But
text.
why does it not matter that where is it from? Because you have one vector is from the image, right? Your A is from the image, the other is from the text. The random should be from one which of the category or why.
So suppose you have a cat, right? So this is your image A, right? You can convert it into an embedding vector A. You have a text. The cat is sleeping. This is your B, or sorry, similar. This is your similar vector. Out of this, you create E similar. You need to create something that is different from A. All you can do is you could take a statement like the hammer worked well, some random statement. Think about it this way. There is no reason E up R should be close to EA, isn't it? You just take a statement that you assume is far from it when it comes to training for contrastive loss, isn't it? That's all. Something that you know is not similar to the image. That's all. If you randomly pick something off the web, what is the probability that it will be about a cat? Well, cats are very common on the internet, but let's say. You get my point, right?
No, I guess can we also, instead of this, can we take an image of like a crocodile, for example?
You could do that. You could do that. The problem with doing that is a crocodile and a cat actually do share similarities. Okay. And not only that, it will be your burden to find such an image that is truly different.
Or let's say a house or a mountain.
You could do that. You could do that also. They didn't do that, but you could do that.
The cat image and the caption for the text for the image is it need to be same for both the search. Meaning like the cat is just image.
Yeah.
For the cat is because of supervised learning.
Yeah.
That for that image, the caption is given. Text is given.
Yeah.
When you say the multimodal,
Yeah.
text is going that the text is the caption of that is going to be a text input.
Yeah. So guys, yeah. So let me go through this. Huh? Let's go through the two phases: training versus inference. Right? A training, what do you need to do? You need to give a pair: image, text. The third part, random, you can just pick up from anywhere. These two things are both needed. Usually it is an image and its caption. In simple terms, image, caption. Okay. You can do. But at inference time, you have created a machine that now clip. What does it do? You can give it either a text and it will create a vector out of that. Let me call this T, just call it T. It doesn't care. You give it a text, it will create a vector. You give it an image, I, it will create a vector EI. It doesn't care. At the end of it, what you get is a vector, isn't it? You don't have to give it jointly. In fact, if you remember, when we did search, what did we do? We just, for example, if you want to use text to search for images, you just give it a text. It became a vector. You compared that vector against all the image vectors, right? Now, the reverse situation also, you gave it an image. You guys remember the Jupyter notebook, right? You gave it an image and you said, okay, find all the text that matches that, right? We gave the image of a golden retriever and it came out with beautiful text associated with the love of dogs, right? Etc. So, because it's just doing vector search. So you can give it either image or text. It will convert either. So that is why it's multimodal. It will treat both of them equivalently. It will just give you a vector representation of whether it's a text or an image, it doesn't matter. Go ahead, Mandeep.
Training would be like done by a CNN, for example.
No, not a CNN. These are VIT. VIT was a transformer. Remember, we did the VIT, right? 16 by. Did I not do a VIT last time? We did do that. Yeah. Okay. So VIT. CNNs do not achieve this level of. See, you need attention. Attention is very important, right? So you need a neural network that has capacity for self-attention. You could do it with CNN, but you'll have to throw in attention somewhere. Are we together, guys? Right. So may I request you this? On the course portal, you will go and see this visual embedding section. This is a paper. I want you to carefully read this paper. This is the easiest of the lot. In the afternoon, we'll do slightly harder papers. Can you guys form your little teams, like your teams that are there, groups of 4 or 5 that you are, and collectively discuss this paper? Yeah. Yeah. So I'll show you that this paper is there. Where is it on our course portal? Let's go and check it out.
Left side bottom.
Yeah,
Side bottom.
left side bottom. Yeah, that's
Yeah,
right.
research paper.
Right. Oh, no, I can see more than you guys can see. Sorry, because there's a lot of the course, just so as not to scare you, I've hidden all the things you'll learn in this course. So here we go. Visual embeddings and image caption. Right. So guys, I've explained the papers that we are going to do today, but I'm deliberately going very slowly because we are breaking into new ground. Read this paper, then we'll read this and this and this. Are we together? And as you do this, here's an exercise, guys. Go back and review the search notebook where we did use clip to search for images, right, together. And lastly, I expect you to try this, guys. Use the Hugging Face code and use clip. Come up with some good use for it. What would you use it for? Right? No, it won't generate. It's not a generative model. Remember, it's encoders. It's a matcher. It will help you search. It will create vector embeddings and so forth. It's not a generator yet. But for example, given an image, could you search for a text that matches it? Or given a text, could you find an image that you... But think of some practical use cases where you can use it. Propose those ideas. Yeah. Go ahead. Oh, yeah, out of battery. Hang on.
Okay. Yeah, I'm okay.
Yeah.
So one of the use cases I feel like the use case is in my computer folder contain 1,000 images, for example, different
Yeah.
photos. It's
Right.
because concern for the family, let's say when you're doing a party or something, they want to get all the picture of the person.
Absolutely. Absolutely.
So, can we make a tool from that image?
Yeah.
In those photos to
See, yes, I got your point. It is doable. I would strongly encourage you to do that. See, do this thing, guys. You need some labeled images, right?
Yeah.
Some vector embeddings in which you say that this is your kit and so forth.
But we need to train that basis.
What you'll have to do is tag or caption some of the images, right? And then just slightly fine-tune the model. Once you do that, it works quite well. You can do that. Right? And also but in this course, you'll learn other techniques that does that particular thing better. We'll come to it. But anyway, guys, I hope I opened the door to multimodal learning. How many of you like it, like this new world? So it's fun, actually. It's just amazing what you can do with that. And go play with this notebook LM. So you have an idea what is it that you have to build. And how many of you like this project? Looks like a fun project to do. Make sure your version is better than this. All right, guys, I'll stop and I'll give you guys a lunch break. We'll meet after that. Those of you who are remote, any questions before I stop?